So in this problem, you are going to use a sequence of multiple reactions you have seen earlier to make a product that is asked here. So combine reactions in equation 3.53 with a nucleophilic substitution reaction to produce this product from this is what the question says, right? So equation 3.53 is the equation that I have shown here, and this is one of the reactions that was discussed in chapter 3. So it concerns the acidities of alkynes. So alkynes, as we have seen, is going to have a carbon with a triple bond, and that means the carbon is sp hybridized as opposed to sp2 or sp3 hybridized. So when you have an sp hybridization, you have 50% s character and 50% p character, and more s character you have, more strongly the electrons that on that carbon is going to be held by the carbon's nucleus. That means this carbon is going to have a stronger hold on these two electrons here, and therefore even a base like sodamide is able to react as a base with this alkyne, and therefore you will lose a proton from this molecule, generating an anion which is going to be unusually stable because you have a stronger amount of or a greater amount of s character on that carbon. So this is one of a really good ways to produce the acetylide anion, something again we have seen earlier in table 6.1 when we discussed that in the classroom. So if you take an alkyne, treat that with a really strong base like sodamide, you'll be able to get the acetylide anion. And another reaction that I would also want you to remember is producing, in a similar situation, producing a sulfide anion. So if you have, say for example, a thiol. Thiol is an SH group, and you treat that with sodium hydroxide, you will be able to produce the sulfide anion. And this is also really good nucleophile, and this is very similar to what you're looking at here, where you start with an terminal alkyne. When I say terminal alkyne, I'm talking about the carbon-carbon triple bond on the end of the carbon chain where you have a hydrogen on one side, and when that reacts with the base, you can produce a carbanion, and so the base abstracts a proton, so the NH2 minus, being a base, abstracts a proton, becomes NH3, and the sodium countercation becomes part of the organic structure now, and you have sodium acetylide, and this is a really good nucleophile, as is the sulfide that you see here. So either way, we're going to now take advantage of this reaction to make this product here. So if you want to make this product from the reactant that is shown here, you have to realize that this is the leaving group, therefore the phenyl CH2 is here, the phenyl CH2 is here, and now this part is going to be coming in as a nucleophile. So if you want to make this a nucleophile, we have to produce a carbanion, the C minus, which is basically that. So we have to start with that and react that with the benzyl bromide to give you the product we have. So that's the CH2 of the benzyl, the bromine has gone, so that is the acetylide part of the molecule. So if this is, say, carbon 1, 2 and 3, and if this is carbon A attached to a phenyl ring, that is carbon A, that is 1, 2 and 3, and this is obviously a substitution reaction, and you can expect this to be an SN2 reaction because we have strong nucleophile and we have a primary carbon as well. A primary is a less hindered carbon. It's a carbon that is not going to be able to maintain a positive charge very efficiently. At least that's what you want to know for this class. Things are slightly different when somebody takes a 2-semester organic. They're discussed in much more detail there, but all you need to know here is it's a primary carbon. Primary carbon favors an SN2 reaction. We have a strong nucleophile that is also going to favor an SN2 reaction, so it's going to be an SN2 reactivity, and this is the product you will see. And as long as using equation 3.53 is concerned, you will make this acetylide by reacting that with the propyne We'll treat that and react this with sodamide, NaNH2, Na plus NH2 minus. This is a really strong base, and often it's done in liquid ammonia because you cannot have an extremely strong base like sodamide in a solvent like water or even alcohol. So sodamide is an appropriate is a strong base that's used in liquid ammonia. And you have the deprotonation, and this produces ammonia. NH2 minus abstracts the hydrogen here, becomes ammonia. Sodium becomes part of this organic anion, and that is now a nucleophile. Reacts with this carbon. The bromine is going to leave, and you get this, and then you get sodium bromide as a byproduct of this reaction. So that is the first part. Now we are going to use the same approach to make this compound that you see here from the appropriate alkyl halide. So if this unit was brought in as a nucleophile based on the reaction we just saw, then again you're going to have the 1, 2, 3 carbon chain as the nucleophile, and you're going to attach that to a 2 carbon chain. Therefore we are going to use, I'm first going to look at the acetylide again. So take the propyne, react that with sodamide in liquid ammonia. That gives you the acetylide. And now react this with 1, 2 carbon iodoethane, and therefore it's going to donate electrons to that carbon, so the iodine leaves, and you end up getting that. So this is 1, 2, this is A, B and C, A, B and C here. So that is A, B and C, that is 1 and 2. So that's how you take advantage of the acetylide formation reaction to attach different carbons to a leaving group containing molecule.